Hello friends, good morning and good evening everyone. Your ALP here. Welcome back to our channel ALP Talks. So today I am here with one more good interview with Mr. Zainab. So she is already we interviewed last time. So this time we are with her MTech project. Wonderful project, direct torque control of AC motors and its proposed methods. So this method mainly used for closed loop control of AC motors for reducing torque and flux ripple effectively. So this is the main theme, and duty cycle control and virtual voltage vectors. That is the main technique we are using in this project. So welcome her and discuss with her so that she can we can discuss all the things in a better way. Yeah. So keep watch this video till the end, and if you're watching this video for the first time, then do subscribe to this channel so that whenever I'm uploading videos, you will get notifications. You can simply click and watch it. Yeah, keep watching. Hello.
Hello, sir. Good morning, sir.
Yeah, good
Sorry
morning,
for
Zainab. Yeah, it's okay. Okay. So how are you?
my laptop. I'm good, sir. Good.
Yeah,
So
welcome
what
back.
about you?
Yeah, I'm also good. Welcome back to
Thank you,
our
sir.
channel, ALP Talks. So your second time we are discussing again with some good stuff. Huh?
Yes, sir. Yes, sir.
Very nice, very nice. Yeah. Okay. So you can proceed here. So meanwhile, in between, I can ask some any have any questions or any discussion. Otherwise, you can keep on continue. Please proceed. You can share the
Okay.
screen if you wish.
Yes, sir. I'll share my screen.
Yeah.
1 minute, sir. It is sharing.
Yeah. I have to enable it. Yeah. I
Yes, sir.
think you can do now.
Okay, sir.
Yeah.
So is my screen visible to you now?
Yes. It's visible.
Okay, sir. Okay. 1 minute. I'll
Yeah.
just start it.
Okay. Yeah.
So shall I start?
Yeah, you can proceed, Zainab. It's very good. Yeah.
Okay, sir. So, hello everyone. This is the topic we are going to discuss today, which is direct torque control of AC motor and their proposed methods. Myself, Zainab Iqbal. So, today I'm going to go with this topic only, which is emerging nowadays more in our industries.
That's true.
What is the motivation for our topic and for today's discussion is first we'll see why we are moving towards AC motors over DC motors. Then what is the
Okay, proceed here. Yeah.
motivation for today's topic are why we are using AC motors over DC motors. What is the need of control method that we are using? Then we'll see what is direct torque control and what are the proposed methods, just like duty cycle control and
Yeah.
virtual voltage vector that will apply to DTC. At last, we'll see the MATLAB Simulink results and the summary and future scope of the topic.
Okay.
So first we'll see why we are moving for the AC motors. First for induction motors. So I'll
Yeah.
say over last many decades, DC motors were used widely for variable speed applications due to its decouple control of torque and flux
Yeah.
that can be obtained by armature control or field oriented control. But due to many disadvantages due to the presence of brush assemblies and commutator,
Yeah.
DC machines have been outdated nowadays. So we are moving towards AC motors. And why induction motor specifically? As due to its robustness, it has less maintenance, it needs low cost, it has high performance, and it is rugged in construction, and it can operate in any environment. And when we talk about three-phase induction motor, it is self-starting. So it is used widely for all these reasons, and we prefer squirrel cage induction motor over slip ring induction motor more because of its rugged construction.
That's it. Yeah.
And then we'll see why we are using PMSM. So for PMSM, we use that in now electric vehicle is emerging nowadays more. So it can be used in automobile industries also. It has high power to weight ratio. It has low volume. It has high efficiency. It has high power factor. We can operate it in wide speed range, and
Yeah,
it has fast dynamic response.
that's true.
So what is the need of control methods? So it is difficult to operate in the AC motor at its highest efficiency. So this is due to its complex mathematical modeling and also its non-linear characteristics during saturations. So because of all these methods, we need some control method which we can implement in practically. So for now we'll see what is actually direct torque control. So the
Yeah.
basic concept behind direct torque control is to control directly the stator flux, linkage and the electromagnetic torque simultaneously. In this
Okay.
method, the stator voltages and stator currents can be controlled indirectly. So this method is having high dynamic response. It consists of that we'll see further also. It consists of two hysteresis controller, one two VSI and the lookup tables. We'll see that now further. So it does not require any current regulators. It is very simple to implement, and it does not require any coordinate transformations. So
Okay.
it has more advantages than the vector control or field oriented control method. So
Okay.
it does not depend on motor parameters except stator resistances. Okay,
Mm-hmm.
so we'll see the first small history, how it came and when it came. So DTC was developed in 1984 and 1985 by Japanese researchers Takahashi and Noguchi, and also by one German researcher, which is Dependrog in 1985. So
Okay.
according to Dependrog research, low harmonic stator current with low switching frequency is produced, and thus more suitable high power application can be used in this method. It is
Okay.
also widely known as direct self-control according to the Dependrog. And according to German research, Japanese researcher Takahashi and Noguchi, switches at relatively higher switching frequency and produces circular flux locus. So thus
Okay.
results in an almost sinusoidal stator current. So according to Takahashi and Noguchi, while applying DTC, we can get a almost sinusoidal stator current, which means harmonics can be reduced by many means. So this method was controlled commercially first by ABB in 1995.
Okay.
So one see the what is basic principle of DTC. So DTC it is a variable frequency drive closed loop control method. In
Okay.
this scheme, we can control this electromagnetic torque and stator flux linkages directly and separately. And the motor flux can be the stator voltages and current can be controlled indirectly. So what
Okay.
happened in this? We there are two hysteresis controller, flux controller and torque controller, which I'll explain later.
Okay.
So in output of these two controller along with the sector in which our voltage vector is lying, these three things we put in by the make these three things will make our lookup table, and output of that lookup table will appropriate voltage vector will go to the inverter, and the output of that inverter goes to the motor. This is how it works. So this is
Okay.
a block diagram. This you can
Mm-hmm.
understand nicely. So these
Okay.
are two hysteresis controller: torque hysteresis controller and flux hysteresis controller. Torque
Okay.
hysteresis controller a three-level comparator, in which if the output of this error, like reference torque and the estimated torque, if the output of this error is greater than the upper limit of this band, then the output of this torque hysteresis comparator will be +1. And if
Okay.
this error lies between the bands, output will be 0. And if it error lies below the lower band, then output will be
Minus
-1.
1.
This is, yes, sir. This is how our torque hysteresis comparator works. And when we come to flux hysteresis comparator, it is two-level comparator. So if the error between in the reference flux and the estimated flux is greater than the upper limit, it will give +1. And if the error is lower than the lower limit, it will give -1.
Minus 1.
Oh, yes, sir. So along with this two outputs, we need one more input for the switching table or lookup table, which is the sector in which our flux or voltage vector lies. Which I can say I'll explain how this sector comes later. So output of the switching table or the lookup table goes to the inverter. It is a two-level, three-phase voltage source inverter. The output of this inverter, this lookup table has been injected to the inverter as gate signals. So
Okay.
output of this inverter goes to the AC motors. Either it is induction motor or permanent magnet synchronous motor. Okay. Then through the output of induction motor, we can estimate the flux and torque from the parameters of the AC motor, what we will get. So these
Okay.
estimated values can again be used as for errors. So this is how our closed loop works.
Okay. Here ABC and alpha
So
beta are frames, right?
yes, sir. It is just one coordination. 1 minute.
Okay.
Yes,
Yeah.
sir. It is one transformation that we use generally in PMSM
Okay.
for converting into axis.
Okay.
So this is two-level phase inverter.
Mm-hmm.
In which it is conducting in 180-degree conduction mode. So
Okay.
if upper switch on, it will show 1. And if lower switches are on, it will show -1 or 0.
Okay.
Whatever people take. Okay. So if upper switches like S1, S3, S5 are on, it will give 1. And if S4, S6, S2 are on, it will give 0.
Okay.
So this is how it is conducting. Then this is how we'll get a sixth sector or
Okay.
a voltage vector. So I'll explain one. So suppose for V4, I want 100. 100 means that S1 is conducting, S6 is conducting, and S2 is conducting.
Okay.
So if upper 1 means upper switch is on, that means S1 is on, and 00 means lower
Switches are
other
on.
legs.
Okay.
Yes, sir. So S6, S2 are on for B and C respectively.
Okay.
So when S1 on, it will output of VA and it will be 2 VD by 3.
Mm-hmm.
So 2 VDC by 3, it is in A phase only.
Okay.
When S is on, that means it is minus VBN. So
Okay.
minus VBN minus VD by 3
Okay.
in opposite direction of B phase. And again 0 means S2 is on, that means minus VDC by 3 in C phase also.
Okay.
So it minus by 3 means in opposite to C phase, minus VDC by 3. So when I get the resultant of these three, I will get the output of that vector. Similarly, I can make the other vectors too.
Yeah.
So this is the lookup table, that is how I make and what is the meaning of other values. I explain it for V4. We can make it for other V1, V2, V3 and other vectors also.
Okay.
So this is the control strategy that I am using in DTC.
Okay.
So this is one of the equation of torque. This is one of the equation of torque that I have used. There are many other equations also that we can use. So we can see torque depends on the angle between the stator and rotor flux.
Okay.
That sine and flux, if I neglect the resistance, then flux is the Vs delta Ts. Ts is the sampling time period.
Okay.
So I neglect the stator resistance. If the stator resistance was also there, then it is the integration of Is, Rs, and Dt.
Yeah.
So for easiness, I neglected the stator resistance part. So let us suppose in sector 1, our vector is this, which is shown by psi 5.
Yeah.
This one. Okay. And if I choose the vector psi 2, the
Mm-hmm.
resultant flux will increase, as you can see.
Yeah.
If I make a resultant flux will increase, and if I see the angle between the two fluxes, which is also increased, that means our electromagnetic torque is also increased.
Grazing. Okay.
Yes, sir. So this is how we can choose our appropriate voltage vector, whether we want to increase or decrease or make it neutral. So for that, I use these two lookup tables, the first flux and torque lookup table, which I have been using. So for increasing or decreasing or making it neutral, which voltage vector should be used?
Okay.
Whether I want flux and torque. So lookup table, which I have, which is the main lookup table, which is shown as switching table in the block diagram, which is I have been used is this. Flux is like air, flux hysteresis comparator is giving me 1, and torque hysteresis comparator is also giving me 1, and my vector is in sector 1. So output, so which voltage vector I should choose? It is V2.
Okay.
Similarly, if one combination is there, and if it is in sector 1, then I should choose V0.
Okay.
For these, similarly, I made every other combination of this lookup table. So this is the MATLAB Simulink result of flux trajectory. Our x and y axis, it is plotted in XY plot. So it is the flux trajectory which is being followed. And this is the output of classical DTC for
Okay.
induction motor. And so in this, you can see first one in both the cases is stator flux linkage is output.
Okay.
Second is the torque, and third is the speed response, which is in RPM. Okay.
Okay.
So in this, you can see there is some like some drops in the stator flux in for induction motor. A is for induction motor, B is for PMSM, and you
Okay.
can see the yeah, torque is 1.153 in induction motors and 1.859 in PMSM. So it
Okay.
is much more when we go for practical case. That's why we are moving towards our proposed methods. One
Okay.
more thing we'll notice, THD, which is total harmonic distortion. So THD is like 23.10% it is coming, which is very much more. It creates more harmonics and it creates more distortion in our output.
Okay.
So these are why we are moving towards the proposed methods. So first we'll see what are the advantages and disadvantages of DTC, why we are using it. So firstly, it does not require any coordinate transformation. It is very easy to implement than other methods, and it does not require any modulators, or if required,
Okay.
it requires very less modulators than other methods. It contains very less number of tuned parameters. It
Okay.
does not vary with the variation of parameters. Like it can vary only with the stator resistance. As I have told you, I have neglected stator resistance in flux equation, but if I can take it,
Okay.
then it does depend on stator resistances, and it has very excellent properties of regulation without any rotational speed feedback.
Okay.
So there are some advantages. First is it has variable switching frequency due to the presence of hysteresis controllers. It
Mm-hmm.
has poor performance at low speed. It has problem during change in torque command. Like it that transient period, it will create harmonics in transient period.
Okay.
And it requires in classifying sectors in which our flux sector works. It has high noise level and it increases with the load, which can be also overcome by some other methods. So
Okay.
what are the need of, as I have explained, there are some disadvantages, mainly which is a variable switching frequency with high torque ripple. So for reducing the ripple and making a frequency constant, I'm using my duty cycle control method. So,
Okay.
okay. In this method, duty cycle control, it is not a method. It is, we can say it is a method which is applied to DTC.
Okay.
So in this method, as in classical DTC, we have seen that the active voltage vector and the zero voltage vector has been continuously applying to to our inverter. But
Okay.
in this method, we are not applying it continuously. Rather, we apply a active voltage vector for some time and zero voltage vector for rest of the time period in one sampling period. So
Okay.
this method will use the torque and flux ripple which has been occurred in conventional DTC. Zero voltage vector is applied besides active voltage vector to change the time period. And optimum time period, which or the optimum duty cycle, is been calculated after every cycle to assure that the ripple should come less, error should come less.
Yeah.
So this is the block diagram of DCC applied to DTC. So this is similar to the case with conventional DTC. Only extra block we are using, which is duty ratio calculation. So
Okay.
duty along with the switch, like his flux hysteresis controller, torque hysteresis controller, and the sector calculation, we are using one more block which is duty ratio calculation, so that we can know which vector should be applied at what time.
Okay.
So this is how I calculated my time periods. So when you see the first formulas, which consist of hysteresis band HB. Okay, HB is the
Okay.
hysteresis band of torque hysteresis controller.
Okay.
And T is the error in torque, TS is the sampling time period. And Tk is the time period when active voltage vector is applied, and T0 is the time period when zero voltage vector is applied. So
Okay.
as we can see in a first this for, formula, the time period depends on the hysteresis band. So due to the error or the ripple in torque will again come more as the band limit changes. Then the
Okay.
error also changes. So to overcome this problem, we are moving with the second formula, which is Tk equals to DTS.
Okay.
When error in torque less than the hysteresis band limit of torque comparator, where D is the duty cycle which has been calculated, and it depends on a constant also. So this is the output, and by seeing only you can see the TS, the output ripple in the output reduces much more. So you can see torque ripple in induction motor is 0.4411, and
Yeah.
in torque ripple in is
0.91.
0.912.
Yeah, it improved a
Which
lot.
was 1.859. So it
Yeah.
improves a lot, and the stator flux waveform also becomes very smooth.
Okay. Yeah. Yeah.
So the advantages. And in when we come to the TSD, it is 23.04% only, which is not much less than the conventional DTC, which was 23.11%. So
Okay.
TSD does not improve by this method, but
Okay.
torque flux ripple reduces much more. To
Okay.
rem- in to decrease the THD or to improve the motor performance, we again go with the other proposed methods, which is virtual voltage vector. So first we'll
Okay.
see what are the advantages. As I have already told you that it can reduce the torque ripple, and we can apply the active voltage vector and zero voltage vector, not for not for all time, but for less than the sampling time period which we have calculated.
Okay.
And also it can be used for a constant switching frequency also. So disadvantages is that in classical DCC method, there is always a challenge to determine best active or the appropriate active voltage vector, which will be best to apply to get the
Okay.
in braking mode of motor in this presentation. And this method drives the torque to operate around the higher limit of hysteresis band until normal motoring mode arise again. That means the error will increase more if it operate around higher limit of hysteresis band.
Okay. Yeah, proceed, Zainab.
And to duty cycle control using 6 virtual voltage vector. So how I am using 6 virtual voltage vector is, or how I am making virtual voltage vector is, as I have shown this V1, V2, V3, V4, V5, V6 and V7 and V0 are the active or the actual voltage which we have. Okay, so we have to make virtual which does not exist practically, but we are making it virtually. So how we make VA, VB and so on. So if I conduct two active vectors as shown in this diagram, when V1 and V2 are applied for equal time period, like TS by 2, TS by 2, then I get a result other vector which I am saying it as a VA, which is known as a virtual voltage vector. And how I get the value of VA theoretically by applying the volt second balance as shown here. V1 T1 plus V2 T2 is equals to VA TS. By applying TS is the sampling time period. So if I apply T1 and T2 for TS by 2, TS by 2, that is equal time interval, then I get the value of VA as root 3 by 2 VDC. So this has been calculated by applying the volt second balance.
Okay.
So this is similar like this. The other block diagrams and everything is similar to classical DTC. Just algorithm is changed. So this is how in this you can see the waveform has become more smooth, and the transient response in the speed you all see it is also improved. Ripple is also improved, like it comes to 0.3733 in induction motor and 0.9034 in PMSM. And
Okay.
flux waveform is also improved, and the ripple in the flux is also improved, like it is 0.002369, 0.00425. As you can, by seeing only, you can see the waveform has been improved much more.
Yeah.
And this is PhD when I am applying the 6 virtual voltage vector only in the lookup table. So it reduces to 20.31% compared to 23.11% in classical DTC.
Okay.
So again, I am moving the 12 voltage vectors. How 12 voltage vector works. I use 6 virtual voltage vectors, which I have explained how I made, and the 6 actual voltage vectors, which is active voltage vectors.
Okay.
Okay, so this is how our 12 vectors I got, and our sectors also changes if I am increasing the number of vectors. So this is the schematic of 12 voltage vector, and this is the result. In this result, you can see the torque ripple is been reduced. By seeing it can be slightly like it is not like it is not good to see. It is not
image seems same, but if you observe closely, the values are less.
Yeah, the values are less, and that is been very much less than the like it was, I think, 1.859 PMSM and 1.2 something for induction motor,
Yeah, yeah,
which comes to 0.2515 and 0.8797 respectively in torque ripple.
yeah.
And in flux also it is reduced 0.001771. I hope it is, these values are visible to you, sir.
Yes, 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 visible, visible.
And the transient response also improves in this by applying these methods.
Yeah,
And we can see the TSD also reduced to 17.20 by applying 12 voltage vectors.
yeah, almost
Now,
6% reduction. Yeah.
yes, sir. Yes, sir. Now we'll see more number of voltage vectors, like 18 vectors. So
Mm-hmm.
12 virtual voltage vector and 6 actual voltage vector. Virtual voltage vector, how I'm making it algorithm, I'll say. When I applied the active voltage vector for if I'm applying the V4 or V2, I can say, when I'm using classical DTC,
Mm-hmm.
2 TS by 3 and TS by 3 time period, and
Okay.
also TS by 2 TS by 3 time period, then I'll get two virtual vectors, that is VA and VB.
Okay.
Similarly, if I go with other active vectors, I can make two virtual vectors in each sector. So that is how I am getting my 12 virtual voltage vectors along with the 6 actual vectors. So I am
Okay.
applying total 8 voltage vectors in my lookup table.
Okay.
This is the square diagram for 18 voltage vectors, and this
Mm-hmm.
is the output which I am getting. So it is
Yeah.
the least among all, 0.2203 and 0.8563 in the torque ripples, and in flux you can see it is 0.001675, and the smoothness also you can see in these diagrams, in these results.
Okay.
All these are been implemented using MATLAB Simulink. And the
Yeah.
TSD, if you see, this is much more. It is coming as 12.41%.
Yeah. Yeah. It reduced a lot.
So, you are assuming like why I am using more and more number of
Yeah, it is
virtual voltage
difficult, right?
vectors.
I
I
mean,
have,
processing and everything will take more time. Did you get more, I mean, faster response? Because you are going to calculate so many parameters. Is it okay? I mean, because you are keep on
yes, sir, yes,
increasing
sir.
the samplings, multiple things.
Yes, definitely. And you can implement much more things, like I have implemented thing. I have made more number of vectors. Why I am saying more number of vectors is useful.
Mm-hmm.
Though it is some like not easy to implement, but by increasing more number of vectors, you can see the ripple and the smoothness in the waveform. If a smoothness in the flux means the smoothness in the current waveform also.
That's true.
So
That's true.
that's why we are using the that's why we can see the decrement in the THD. And if
Okay.
I increase more number of vectors, that THD will also reduce much more, as 23.11% to 12.41%, almost 50%.
That's true.
I can say. So these are the advantages, that current waveform becomes smoother, flux waveform becomes smoother, torque ripple and flux ripple become reduce drastically, our transient response become good, and the efficiency lifespan of motor becomes good. THD is reduced comparatively.
That's
So
true.
all that was my work. I hope that was not boring. So I just summarize it, that we have seen our classical DTC method and how we are using AC motors overcoming DC motors, and how it
Yeah.
is better than vector control method, as it does not require any coordinate transformation and all. So, but there are some limitation in DTC, that we have seen a torque ripple, flux ripple,
Yeah.
THD problem, variable frequency problem. To overcome all those problems, we have used some proposed methods, and we saw that those problems are really overcoming by these, and all these results are taken through MATLAB Simulink only. and the results have been compared. So what are the major things that we want to know through any project is what are the future scope, how we can use in these things in future. So I have used PI controllers in this. So I can use, if I can apply the artificial intelligence or the ANN fuzzy logic instead of PI controllers, then that will be more reliable. First of all, ripple will be less, response becomes more smooth. It can be used in real-time applications such as robotics, and it can be used for implementation of constant switching frequency. That is the major, like why ripple is coming more due to the variable frequency,
Yeah,
switching frequency.
that's
So
true.
if I use, if somehow I can implement a constant switching frequency in this method, then my most of the problem will be solved, and it can be applied in electric vehicle using PMSM and SRM. An AI based controller will be more efficient than other in PI controller that we are using. So these are the some future scopes. So thank you for the listening
Yeah.
me. Uh,
Yeah, it's a wonderful,
this
wonderful, Zainab. Very good presentation. Yeah, so you covered
thank.
most of the topics. Yeah, I have a
I
few.
hope it.
Yeah, yeah. You can disconnect this sharing. Yeah, yeah. So
Okay,
it's
okay, sir.
yeah, it's a very nice. So I have a couple of questions for you. I mean,
Okay.
so generally, how much time it taken for you? I mean, for these simulations and all. Are you already an expert, or you started everything learning, or how? What's your experience on it? The learning
Yes,
process.
sir. Yes, actually, this was my major project in my master's. So
Okay.
yeah, I have completed in a year, but I have done many other things along with this project. So
Okay.
you can do according to your wish. Like it is like how dedicated you are towards your work. You can
Okay.
do in that much time period only. So first,
Okay.
I have started with reading some books based on DTC. I learned firstly how DTC, what is DTC actually. I have read
Mm-hmm.
some good research paper, many research papers.
Okay.
Whatever comes to me, I just read, and then I sorted out which will work for me, and I try to understand. Like it will take
Okay.
learning will take much more time than implementation.
That's
But
true.
once you have learned all the concept, then you can implement by applying your own logic. It is not like what I have applied and what is been applied in all the research papers and some books.
Yeah.
So that is not necessary that you have to apply that logic. You can apply your logic like I have done through modeling. You can go with the
Coding.
coding also.
Yeah,
Yes,
yeah,
sir. You can go with your own logic. You can go with your own algorithm.
yeah.
So it is depends on you how your how much time you are taking. Yeah, it will take some time because of thinking, and also when you apply your logic and algorithm, then the main things come. Then error will come.
Yeah,
Sometimes error will not come. You are getting the result, but you are not getting the exact result what you want. So you
yeah,
are not knowing where error is coming. Then again you have to go through this.
yeah,
So
yeah.
one suggestion I'll give if anyone is making it, while making, just make small part and check continuously your result, so that
Okay,
at last if you're getting any error, you can you know that where your errors are coming from, in which section your error can come.
okay.
So this is the yeah,
Yeah, yeah. So I developed in a Simulink, right?
yes, sir, I have developed all this in a Simulink.
Okay, okay. Yeah, for the motor, induction motor or PMSM motor, I mean, have you assumed like
Yes.
ideal one, or you given some many ratings like 5 HP or something like that, or you
Yes, sir,
considered
I
like
have given.
everything one, or what? What is your considerations about that?
You can consider rating from your laboratory, any motor from your laboratory, or any from your research paper also. You can take ratings, and I prefer to take practical values
Okay,
than applying just ideal values. So I took
okay,
practical values.
okay, okay, okay. Yeah, I mean, in most of the slides, it's mentioned like fundamental frequency 16.67 like that. So why you went
Yes,
for that frequency? Is this a suitable frequency for electric vehicles or what? Generally 50 or 60 hertz will be there, right? Most of industrial cases.
yes, sir. Yes, sir. It is 50 hertz, but when I go, it is fundamental because when harmonics come, it is say like we even harmonics is not there. Then we go to the Fourier series. I'll
Yeah.
not go with that now. So
Mhm.
third harmonics is the major harmonic that we get. So
Okay.
that is the frequency of third harmonic, or
Uh-huh.
I'm saying it is a fundamental frequency.
Okay.
That
Okay.
50 by 3.
Okay. Okay.
That is
That's.
how that 60.
Okay. Okay. Okay.
Mm.
Yeah, very nice. Very good, Zainab. Thanks for your presence for today and discussing these different things here. Yeah. So we are going to do many more sessions also with the different good topics in the
Yes, sir.
future.
Thank you.
Yeah.
Thank you that you called me again.
Yeah. So you try to refer your some friends or colleagues also, so that they also can be a part of this journey and for spreading the knowledge. Why? Because you spent a lot of your time, efforts, and you made this project. So if any newcomer or fresher or anyone who wants to do these kind of projects, they can simply start from the next level onwards by just observing, and
Yes.
so they can also get guidance from you because you already did some this project. So you are at least the LinkedIn details, some contact details were available for the most of the people. So for example, I have one of my junior who is in Germany. So he has some issues in the model. So he is actually needs the people who are already in that particular area. So like that, so these interactions, these projects, whoever did, so their experience already plays a major role for the other people. So they can contact them and they can rectify any errors, or they can improve a lot. Yeah, that's the main intention of these things. Yeah, thank you. Thanks a lot, dear. We will meet in the next video. Bye. Yeah,
Thank you, sir. Thank you, and have a nice day. Bye, sir.
bye bye. Thank you, friends. This is about this presentation. Yeah, I hope this information is useful to you. If you enjoyed the content, and don't forget to like and subscribe to this channel, and please share this video to your friends and dears to whom it may be useful. Yeah, if you want to be a guest on this channel, then you are always welcome. Then you can simply message me or comment on the video, and I will contact with you, and we can be guests on this channel. Yeah, thank you. We will meet in next video, guys. Bye.